Kukavica, who will talk on the size of nodal sets of solutions of elliptic and parabolic PDEs.
Much for the invitation. It's really nice to be here among friends in Rio, so I really enjoyed it. So I'll talk about some things about nodal sets. So the nodal sets is a synonym for zero sets of solutions of elliptic and parabolic PDEs, and also with particular goal to study the Navier-Stokes equations, but also we'll see ins and outs of studying solutions for equations related to Navier-Stokes. Okay, that's the abstract. I'll just skip that. So the basic goal about zero nodal sets is to take a PDE, any kind of PDE, and then in any kind of open domain, and then ask a basic, simple question: how complicated the solutions look like in terms of how complicated their graphs are. And of course, that could be measured in several ways. We will basically measure how many times they wiggle up and down. So we will study the level sets, u of x equal lambda. But if you're interested how many times the function changes from increasing to decreasing, then this means like in 1D you're studying the zero sets of the gradient. So that's actually included in this kind of stuff. And then you can study for any kind of derivative. If a function solves a PDE, then derivative will solve a linear PDE. So actually, in a sense, you need to be able to deal with quasi-linear PDEs. Okay, more about this later. So if U solves an evolutionary PDE, so if there is time, it makes sense to freeze time and ask the same question. So how complicated the solution is. And the notation we're going to use today is for the nodal sets or zero sets is n sub f. But sometimes I'll just write it whole. Okay, here's a numerical example. So if you take a Kuromoto-Sivashinsky equation, why Kuromoto-Sivashinsky? If you take a second-order equations, the number of zeros, like second-order parabolic equation in 1D, the number of zeros is going to decrease because of the maximum principle. I'm sorry? Yeah, it's not elliptic. If you take what I'm saying is if you take parabolic 1D PDE, like heat equation or let's say Berger's equation, the number of zeros because of maximum principle will decrease. That's called Matano's principle. And in Kuromoto, however, you can see that zeros can be created. Like this bump came out of nowhere and it's going to go up and this one is going to go down. And the zeros do get created and it's a variable of... If you just look at the Kuromoto, you observe that number of zeros is actually fixed number of zeros per unit of time, but that's quite difficult to prove. But that's a matter of another talk. Here is an example of 2D Navier-Stokes from some physics book, I think Lilly. From Lilly, so he took some initial vorticity configuration, let it evolve in time, and then you get steep gradients. But I think that's what he was trying to demonstrate. But you can also see that level sets are kind of stretching, right? So things are happening, and we're going to be interested again how, for example, what is the total length? That's going to be the question. Okay, so that is the motivation, and and actually. If you start with the simplest case to start is the Sturm-Liouville problem, just an ODE, where things are completely clear thanks to Sturm-Liouville theorem. So if you take, let's say, simplest case, u2 derivatives equal lambda u, we know how to solve it due to Dirichlet conditions by sine kx. So the number of zeros for every additional eigenvalue is one greater than the previous one. So it's exactly k, and the lambda is k squared, so expect number of zeros to be square root of lambda. Not expect, but that's the fact for the Sturm-Liouville, and then you can do this for any kind of second-order ODE. So everything is done happily for 1D ODEs. 1D linear ODEs. However, nonlinearity would not make much difference if you're interested in upper and even lower bounds, because lambda being a function, it's not a problem. So you could as well do, for example, if you had a nonlinear PDE, you'll take one derivative, you'll have a linear one, apply Sturm-Liouville, and you will know everything about zeros as far as upper and lower bounds. Unless if you're happy with things up to a constant. Okay, so that is the general thing you can do. So I will not study this today. In the higher dimension, we have in higher dimension we have this famous theorem by Federer for real analytic functions. If you take a real analytic function, then the zero set is a countable union of manifolds plus a set of lower dimension. And this is a conjecture given by Yao, which is actually still open. If you take any kind of second order, it's phrased on manifolds, but you can also phrase it for elliptic PDEs. If you take an elliptic PDE, eigenfunction should have the total measure of their zero set less than c times square root of lambda in sync with the Sturm-Liouville theorem for 1D. Okay, so immediately in 2D, it's open, right? So a lot of results were done by Donnelly and Pfefferman, but they were limited on eigenvalues and eigenfunctions. So Laplacian u equals lambda u on real analytic manifolds, then upper and lower bounds are comparable to square root of lambda. So it's a really, really sharp result for real analytic manifolds. And we'll talk a lot about upper bounds. For lower bounds, they come because if you take an eigenfunction, because of maximum principle, again, it has to have a zero in every square of radius 1 over square root of lambda. And then also you cannot have, so if you have a zero, let's say in 1D, it also cannot do this because on small scales, the Laplacian u equals lambda u, it's like a harmonic function, and then that would violate the mean value theorem, approximate mean value theorem. So that's how these lower bounds come about. But it's a very beautiful thing. They also have, for smooth surfaces, they also have upper bounds, which are not, I think, not Yao's conjecture, but maybe lambda to some algebraic power. Their method is analyticity on small scales and combined with uniform Carleman estimates with respect to lambda. I'll talk more about Carleman estimates a little bit later on. So Donnelly did for some eigenfunctions, but it already became more complicated. So, for example, the constant depends on the number of eigenvalues below lambda. In other words, bigger the sum, bigger the constant in front of square root of lambda. And that's because he multiplies the Laplacian minus lambda for different lambdas, and then you get a differential operator of high order whose order depends on number of eigenfunctions you have. Hart and Simon studied the smooth equations. So for smooth equations, the best known bound is exponential. So nobody touched this since '89. So it's e to the square root of lambda is the best one could do. And the trick is to use harmonic polynomials. It's a very beautiful but very technical proof. Han and Lin extended this to the parabolic equations with similar exponential bounds. Then for the Navier-Stokes equations, so that was the very motivating for me result for the Navier-Stokes, and also for the Bernard convection. So if you take the temperature, let's say temperature evolution, it's a result by Constantine 1990. Take the temperature evolution of the temperature, where U is a solution of Navier-Stokes with right side, being the gravitation times T times the constant. Then the space-time averages, so take a level sets and then average in space, average in time, are bounded algebraically in terms of physical parameters. And again, the basic tool, not again, but the new basic tool is the co-area formula. Okay, I will be interested. I'll be interested in things which are pointwise in space. So try not to average. So what can we say? And then, so yeah. So similar bounds were obtained for the vorticity. In 2D, vorticity is a scalar, so it's a very nice scalar function. So you expect level sets to be curves. Nice curves modulo some small dimensional part, and then again the reasonable question is how big can they be. So we need to start with linear parabolic equations. So I'll show you two cases, and then also I'll return to the Navier-Stokes equations toward the end. So by the way, until when am I going?
15 minutes and 9:50.
9:50, thank you. So let's see, so things are better much better for linear equations than semi-linear equations, but nevertheless, we need to see what's going on first on the linear ones. Linear means that linear dependence in U, but A are allowed to be depending on X. In this theorem on X, but you could include dependence on T. You could think that nonlinear equations are included, but as we'll see, a lot of things will depend on analyticity of A. So I'll say what is the difference between, why can't we apply things like this for Navier-Stokes, let's say, first. Okay, so let's take the linear operator of any order, elliptic. So equation is just parabolic du dt plus A equals 0 with Dirichlet boundary conditions and some initial condition. Then the assumptions are, so take the ellipticity assumption on the coefficients, real analyticity in a neighborhood of omega bar. So you assume that solutions are analytic, not solutions, the coefficients are real analytic, and that omega is bounded, a bounded domain with analytic boundary. Okay, under these assumptions, you have a Gardner's inequality. In other words, you can compare the HM norm with the AU norm. You can take this one to be 0 just by multiplying by the exponential. So you can just consider the elliptic case when the principal symbol is elliptic. All right, then the theorem I had some time ago is that the Hausdorff measure of the 0 set or any level set, so the bounds are uniform in mu, so any volume in instant time t is bounded by a constant, so this is just a correction factor, but you have an algebraic power of 1 over t plus integral of a Dirichlet quotient. So Dirichlet quotient is the quotient, like if you have a Laplacian, it's gradient u squared divided by u squared. In general higher order case, it's au comma u divided by u comma u. So this quantity is important for the purposes of this talk and also for many other things. In unique continuation, as I'll mention later on. And both terms have to be here. So let me explain both of them. So the term 1 over t comes because you have no control of how wild the solution is at the beginning. It could have like infinite number of zeros. As you evolve forward in time, solution becomes analytic, so expect finite number of zeros. But since at the beginning it could be infinite or you have no control, there must be a bound of some kind of function of 1 over t. That by itself is not enough because, so this term has to be present too, because if you take solutions, let's say sine nx for the heat equation, so I forgot to have a board here. So if you take sine nx, maybe n is the dimension, so I'll use k, then the number of zeros will remain k for all time, and the solution is going to converge quickly to 0. So bigger the k, bigger the number of zeros, but the solution is converging quickly, and that's exactly the role of this different quotient to penalize functions which oscillate a lot at the beginning. So without both terms, the theorem is false. And actually, the powers are sharp, as I'll show you that it gives you, this is the correct power, and this is also correct power. So it would be really nice to have something like this for the Navier-Stokes equations. The best I could have done so far is some results in collaboration is algebraic power of t and algebraic power of q. But a theorem like this, which might possibly be quite true, is it's not clear how to do for the Navier-Stokes. And actually, the main reason is this logarithmic convexity method. So how does, which answers the question, how does this Dirichlet quotient behave in time as time goes on? So this Dirichlet quotient is a key quantity for many things, including inertial manifolds, which people studied and so on. Yes, please. Yeah, for the pressure, it would be. It's an interesting question. If you look at the pressure, it would be Laplacian P equals U squared, and then you have evolution equation for U. It's definitely an interesting question. I'm just thinking if it would follow from something like this. It's kind of yeah. It's difficult. It's difficult to do this. What I'm going to present for systems. When you have an equation coupling U and V, and then get information for U and V at the same time. So for example, 2D Navier-Stokes, where you have omega being a scalar, is much easier for me than omega being a vorticity, but it's a very, very good question. Yeah? So definitely would be, I believe would be nice to get something like this. So the Navier-Stokes equation, so this Dirichlet quotient, so how does it behave on time, is the reason why actually we cannot get like linear dependence on Q for it. Okay. The Q is a non-decreasing function of time actually. So this is actually bounded by T times Q0, Q times 0, and that was first obtained by Agmon and Nirenberg. But then there were some better ways discovered for treating Dirichlet quotients. I forgot whether I have it on the next or not. I think I don't have it. So if you'd like, very, very beautiful properties are in the papers of Foyash and So, where kind of a new identity relating this Dirichlet quotient was. And then applications to inertial manifold and how to explore this to get spectral barrier method for construction of inertial manifold is the paper of Konstantin, Foyash, Nikolenko, and Temam. Okay, let me show you how from the equations for the heat equation you can get the bound on the nodal sets for the sums of eigenfunctions. So take any kind of sum of eigenfunctions, just think heat equation, it's general enough. And except in 1D. In 1D, you know, number of zeros is increasing, so you can get good theorems. Okay, so you have the linear combination of eigenfunctions, AU, J is lambda, JU, and then you can solve the heat equation backwards and forwards in time, for all time, and that is the solution. And the key is that you have solution for all time, so T is in R, and you have some exponential factor, UT plus AU, and then you apply the previous theorem, you have a choice. We are interested in the number of zeros at 0. We have a choice where to start the T in the past. So we start at minus T0, and then we discover later on by balancing which T0 is the best. So that is the solution at time minus T0. T0 is positive, and then by the theorem, which I showed you, then the size of the level set or zero set is bounded by this. Q is bounded by the maximal eigenvalue for all time, because it's always on the maximal scale is always the same. Minimal scale is always the same, so Q is less than maximum of lambdas, and you plug this in, balance the two terms, you discover this is the best one, and you get the number of zero sets for, it's bounded by constant times lambda to power 1 over 2m. 2m looks like better than the Nelly-Pfeffer, but it's not. If for second order equations m equal 1, you get square root of lambda, which is the improvement of Donnelly's result. He had done, the constant doesn't depend on the number of eigenfunctions, right? But it also covers all the elliptic problems. So the point of this is to see how you get sums of eigenfunctions, but also that you cannot really, that this power is the right one, and these bounds are the right ones, everything up to constant. All right, I'll prove it the theorem, because it's actually simple, and it contains some ideas which should be used then when we do the, let's say, Navier-Stokes equations. So if you take the semigroup, you can explicitly compute it from the operator A using the resolvent. Gamma is some path, suitable angular path in the complex plane. The key is to compute the derivatives in time. So derivatives in time, you have a formula, again, using the resolvent, and you can bound just by upper bounds, and the main step is this, when you estimate 1 over t to the j with j factorial with the exponential, and realizing that actual exponential of an algebraic power is what you're looking for. Why exponential is fine, I'll show later. Okay, so you're able to obtain the bounds for the time derivatives in terms of exponential of 1 over t. The difference is here we have at time t, here we have at time u0. So the first goal is to have everything at the same time t, not t and 0. To relate u0, so this is where the Dirichlet quotient role becomes clear, is to know the solution at the later time based on earlier time. In other words, when you go backwards in time in the heat equation, you need to use Dirichlet quotient. Okay, so the bound on Dirichlet quotient lets you bound the u0 at earlier time with u of t at the later time. In other words, we can bound later time as a... So we're bounding the earlier time with later time using the exponential bound with Dirichlet quotients. Okay, so that bound already pops out. So see, it's exponential of what we are looking for. Okay, so in the step number 1, we're able to bound all the time derivatives of a solution with the norm itself, modulus and factor. Okay, then in step 2 is to go from time derivatives, since the equation is linear, to space derivatives. And this is the trick. So if you relate the time derivatives of u, they're related with the powers of A. Like for the heat equation, you get Laplacian to power j. Time derivatives in time is a 10th power of Laplacian. So we are able to bound any kind of power of Laplacian with this. And that's kind of like analyticity, except you would rather have gradients than Laplacians. And to go from the Laplacians to gradients, there is happily a machine due to Lyons and Magenès in their third book called the Theorem of Elliptic Iterates. It's a very powerful tool for analyticity for elliptic and parabolic problems. So if you have a bound for all the powers of the Laplacian, you automatically get the same for all the gradients with the correct factorials. So it works for analytic or for Gevrey regular functions equally fine. It's a generalization of Agmon Douglas-Nirenberg machine, just keep track of factorials, but it's also something which deals with boundary value problems, so that's another theorem of elliptic iterates. All right, so we have, so the step 2, we got bounds on all the derivatives of u in terms of u itself. And then you can extend function holomorphically. So you see that there are correct factorials here. You extend function into the holomorphic plane based on the analyticity radius, which you see, whatever it's, when you have e to the t, whatever it's next to, whatever it's next to the j factorial, right? So this c to the j, that's the radius of analyticity. Okay, by the way, this is the second case. In the linear elliptic equations, you start with analytic data, the solutions become analytic with positive radius right away. The analyticity radius is not growing, but it jumps. And that's where the difference with nonlinear equations comes in. Like for Navier-Stokes, the equation, things go like parabolically as a worst case scenario, right? Okay, so we bound in a fixed, we are able to extend the function into the fixed strip in the complex plane and this tells you the growth information. And you know from 1D complex analysis that if you have information on the growth of the holomorphic function, you know how many zeros at most it can have. So use the Schwartz lemma in 1D. And you get the correct number of zeros. I'll not go through that part, but it's elementary. It's a very cool trick how to deal with this in higher dimensions. So how the bound number of, kind of everybody knows Schwartz lemma. It's less known how to measure sizes of level sets of analytic functions in higher dimensions. But it's a nice trick of Donnelly and Pfefferman. You basically integrate. So if you have a function with some zeros, what you do is you take a point and you take a lot of arrays and you compute number of zeros and then you integrate. That actually it's not a correct. That's not an upper bound. This way you don't get an upper bound of number of zeros because a lot of zeros could be aligned with arrays. So that's why the first try this is not good. But if you do it for two different angles in 2D, that's enough. So what you do is you take one angle, ray, measure number of zeros, integrate, do it from another one too. You add these two things, and that's an upper bound for higher dimensions. So that's due to Federer, this geometric book trick, and Donnelly Pfefferman used it to estimate upper bounds for the nodal sets. All right, so that is how it goes for linear parabolic equations. So for the periodic case, you can actually make a black box like this. So assume that you have this is not a solution of a PDE. Suppose you have a reanalytic periodic functions with period L, and assume that this Fourier-Stemam, this Gevrey type operator, is bounded by a constant times UL2. Of course, that's not an assumption. M is just the quotient of these two quantities, right? So M is the quotient of the Gevrey norm, or what they call, or we should call it, I don't know, analytic norm, or Fourier-Stemam norm divided by UL2. Then the cardinality of the zero set is bounded by 1 plus log M, so it's logarithmic in the M and exponential in the L divided by analyticity radius. Okay, so you can see that, so the important observation is that the number of zeros, so that's proven by the same technique as I showed you, Schwartz lemma in 1D, and then measuring on rays in higher dimensions and extending complex plane. So you can see that the size of the analyticity radius is very important. So bigger the analyticity radius, better. So if, for example, for the linear PDEs, the analyticity radius is constant, so we get exponential to a constant. So that's why linear PDEs, the last theorem could be so effective. For, let's say, Navier-Stokes equations, what happens if you start with non-analytic data, the solutions grow in time until certain small constant, not general constant, but constant depending on physical parameters. So the bounds you get are finite, but bad. So they're exponential. In order to obtain good bounds on the zero sets of, let's say, something like a Navier-Stokes equation, you need to apply this lemma on scales of the size and analyticity radius. So if you have something like this, on a small scales, like size of the analyticity radius, then you're able to get conclusions which would be more satisfactory, namely you don't have exponential dependence. So we always, the way we try to think is exponential is not good. We try to get polynomial, then try to go toward something sharp, quotation mark. All right, so exponential. So to get exponential bounds, you actually need to compare the L2 norm on a large set with L2 norm on, or some L infinity norm or some LP norm on a small set of the size of the analyticity radius. So, and if you check, since there is a log here, we are happy if you get exponential. So exponential bounds, so in order to get good bounds for a PDE at hand, you need what is called an observability estimate for fixed time. Okay, so if you freeze the time, so take a PDE, freeze time. What you want is the L2 norm on the large set, estimated in terms of L2 norm on the small set of the size of analyticity radius. Okay? And it's a very basic question, can we do this for a given PDE? But it's a very difficult question too, and there is a lot of literature. These kind of things are called unique continuation. So if you know, phrase it in a different way, if a function is small here, is it small everywhere? So that's a basic observability or basic unique continuation question. Or a weaker question, if it's 0 here, is it 0 everywhere? Okay. We know if function is analytic, then this is true, right? So if function is 0, let's say in 1D on an interval, it's going to be 0 everywhere. But the observability we get using analyticity, it's has very big dependence on the size of the scale. Okay, so small dependence is double exponential rather than single exponential. Hence, something else is needed. We do need to use PDE to get observabilities. So there is a huge literature on this, and let's start with the elliptic equation, and then I'll tell you some results about parabolic too. Okay, so the basic 3 tools used for unique continuation is analyticity. Okay, so that's always available, and if the solution, if your, let's say, force in a Navier-Stokes is analytic. Okay, so that's the analyticity, and use Hadamard 3-circle theorems or Schwartz lemma, or it comes in different disguises. However, the people figured out quite some time ago that actually, I think starting with Karleman, that if you take an elliptic PDE in 2D and later on in higher dimension, then solutions, the coefficients don't have to be analytic in order to have unique continuation property. So there is some kind of analyticity built in ellipticity or parabolicity, right? These kind of methods are, there are 2, maybe there are others too, but they're not as amenable to coefficients being different from 0. So they're basically in 2 classes. One is the most popular is the third one, Karleman estimates. So Karleman estimates are weighted estimates on U based on the differential operator with weights, but with constants independent of weights. So because the constants are independent of weights, they're hard to get. And second method on the list is the frequency method. It's about there is something like a local Dirichlet quotient for elliptic PDEs. It's again, gradient U squared divided by U squared. It's on different sets. This one is on the ball and the set. And then if you check for the harmonic function, this happens to be a non-increasing function in R, as observed with an Almgren. There is an analog of these kind of things for parabolic equations as well. So this one came more recently, like in 90s. Kurata and Poon, they found the frequency for the parabolic equation. It's actually U squared weighted with the Green's function. And then Karleman estimates, there is just too many papers to try to mention. I do have, I thought I had transparency somewhere with this. I think they come later, yeah. I have later on more complete, some names associated to this. What I wanted to show is how to deal with the Kuromoto-Sivashinsky equation, which I showed you the graph at the beginning, and then I'll touch on the Navier-Stokes, and I'll probably run out of time as it looks right now. So think of Navier-Stokes equation, but we can start with any kind of elliptic PDE, and any kind of 1D parabolic PDE. For starters, and the method can then be extended to higher dimensions. I'll show you how. Okay, so take any kind of PDE, leading coefficient is 2s, in Kuromoto-Sivashinsky S is 2. Okay, and these are V's. V is a coefficient depending on x, but it can be U and should be U, right? You can think of V being U, like that UUX would be one of the terms. All right, so we assume periodic boundary conditions in a domain omega equals 0, 1. And Okay, so what I'm saying here is if you take any kind of nonlinear PDE, if you differentiate, you get this. Okay, so what are the assumptions? Let's take the PDE. So this I'm going to talk about joint result with Michaela Ignatova. So the Gevrey, we assume Gevrey regularity of coefficients. Gevrey meaning non-analytic. I should have given a definition. So the Gevrey regularity is same as analytic, except that we put different power of the factorial here. I didn't write the definition. Yeah. So for sigma equal 1, we are assuming analyticity. For sigma bigger than 1, we are assuming Gevrey regularity. So Gevrey functions, on one hand, generalize analyticity. On the other hand, they behave differently. So for positive S, for instance, they can be compactly supported, so they don't have any continuation property by themselves. And you can actually make test functions, build off Gevrey functions, and so on. So Gevrey for sigma bigger than 1 is quite different than analyticity. It can also be viewed as a stepping stone toward the C infinity, or towards the usual smoothness we like. So assume Gevrey regularity of coefficients with some exponent, sigma. Then we assume doubling property in time variable, meaning how things are growing in time. So that usually means assuming something on the initial Dirichlet quotient. And we also assume that the Gevrey doubling estimate for U. Again, this assumption is actually follows from 1 and 2. If you know that coefficients are Gevrey or they're analytic, if you know how function is decreasing in time, worst case scenario, then you can actually compare using the many theorems on, again, too many to mention. So you can estimate analytic norm in terms of the norms itself. So this is not a strong assumption. It actually follows from, it's not an assumption. Oh, it's C1, yeah. So C for corollary. All right, so basically we have two assumptions. Okay, then the theorem with Ignatova is, so suppose that U satisfies the assumptions, and assume that sigma is not much worse than analytic. So 1 plus a constant, positive constant. Then the size of the solution on the big interval is bounded by the size of the function a small interval times some exponential of a polynomial on all the coefficients which we have in the assumptions. And exponential, again, bound is what you want. You cannot get better than exponential. In other words, when you take, let's say, number of zeros, which is going to be a statement on the next transparency, leads to polynomial bounds on the zero set. So if you take number of zeros, then the cardinality of number of zeros is less than a polynomial on the Dirichlet quotient, analytic properties, and so on. Let me emphasize this does not exactly follow from analytic theorem. There is no Schwartz lemma for Gevrey functions. So I need to tell you how to count number of zeros for the Gevrey functions. It's a non-trivial matter, I believe. So it's impossible to get something like this for Gevrey functions, again, because Gevrey functions can be compactly supported. Like e to the minus 1 over t squared is a prototype. Like Gaussian in time variable is Gevrey 2. Okay. So here, I'll go through the strategy of the proof without doing much detail. So the reason why this it's interesting is because the Kahleman estimates, if you look at what they do is they provide observability's estimate from open set to larger open set, not for fixed time. Okay. And there is no frequency method that anybody could come up with for the higher order equations than 2. So like the frequency method or Dirichlet quotient method for continuation, it's not known so we need to use Kahleman, but Kahleman estimates work only for open sets, not for fixed time. So what do we do? So take, in the step 1, we take, assume that U is small on some interval for some fixed time t. Okay, so just, and then you prove that all the derivatives are small as well. that's not incorrect. So of course, if function is small, derivatives don't have to be small. But keep in mind we have bounds on the higher order derivatives, so we can interpolate, and this way you obtain that actually all derivatives must be small too, with huge, of course, factorial factors, factorial factors. So step 2 is once we have that all space derivatives are small, then from the equation itself you can get that all time derivatives are small as well. So that's in step 2. Okay, step 3 is now we don't have Taylor series doesn't converge for the Gevrey functions, but somehow it's possible to get, which I'll show how briefly, how to get from space-time bounds on the space-time derivatives to prove that U is small itself. And in the last step, once you have smallness on a rectangle, Kaleman estimates can propagate. So that's step 4 is known. So how to go from open set to open set. Okay, so steps 1 to 3 help you go from fixed time to a neighborhood, and then to the fixed you go with Kaleman. But I'll mention it just because maybe people are not familiar, so it's nice to see something on Kaleman estimates. Okay, step 1 is when smallness of function implies smallness on the derivatives. It's, as I said, it's interpolation. So assume that uj is bounded by some big constant always times factorials, which you need to keep track on, and that's assume that u is small, then all derivatives are small. And as I said, just use interpolation. Step 2. So differentiate now we need all space derivatives, space-time derivatives to be small. So we have to just differentiate the PDE term by term. And by induction, you prove this, and you see the penalties are, in terms of factorials, are huge, but sigma is something just above 1. Okay, so that is true for the x in a neighborhood, and you just need up to some constant. You don't have to pay attention to specific bounds. Important is that there's epsilon here and to which power it comes about. So then once you have the space-time derivatives, you actually, for Gevrey functions, you can use the Taylor series, except that the Taylor series doesn't converge. So the Taylor series, there is an optimal place to stop. So if you take more and more terms, it tends to converge, but then if you take too many, it tends to diverge. So some people call this Borel summability. So you split into, so it's a Taylor, in other words, that's all fancy name for the Taylor theorem with remainder. So take a Taylor theorem and then remainder on these terms, on the main terms, you use smallness. On the higher terms, you need analyticity, and you need to use the factorial, and then you optimize in n. And one technical thing is that one needs to actually do this not on a fixed constant interval of time. It doesn't work this way. The estimates don't close, but you have to actually, the size of the time interval depends on epsilon. Epsilon is the size of the L2 norm, so you get log epsilon. So after some calculations, again, the precise form doesn't matter, but from the lower bounds, you get epsilon to the 1/2, and from the remainder term, you get log epsilon in the denominator. So if you stop at the right n naught, and right n naught is somewhere about log epsilon to a certain power, here it is, and somewhere here, you realize you cannot use arbitrary high Gevrey regularity, which probably the theorem has some, maybe not even true. So if sigma is not too big, so if the Gevrey exponent is not too big, then you can bound all the derivatives of u in the space-time triangle. For technical reasons, it's not enough to bound u. You have to bound derivatives up to 2s as well. So you get this, and both have log epsilon in them. Okay, and then that's in a brief sketch. I'll tell you a little bit about the last step, which actually then it's important for the Navier-Stokes equation for us. So again, joint work with Michaela. So if you look for the Koromoto-Sivashinsky or 1D equations, there is a theorem due to Isakov, which is in turn improvement of a paper by So and Schauer. So Isakov's Kaleman estimate, which in other words, which in other sense, it's also a generalization of Hermander elliptic PDE. Elliptic PDE Kaleman estimate, it's this. So assume that you have weight satisfying certain kind of convexity assumption called pseudo-convexity in some open set in a plane. Then you can bound the weighted norms of U in terms of the elliptic operator weighted norm. So so this is a prototype of a Kaleman estimate, and let me just tell you why this implies unique continuation. The simplest form of unique continuation is assume you have a solution of a PDE which is just compactly supported. Kaleman estimates are all true for compactly supported functions. So if you take a compactly supported function, you plug it into here, you get right-hand side 0, so the left side must be 0, 2, and that's the end. So compactly supported solution of a PDE must be 0 as soon as you have a Kaleman estimate for it. If the function is not Kaleman, if it's not compactly supported, you need to cut it, and then you get a three-sphere type theorem like Hadamard. So that is, in a nutshell, how things go. Okay, when you have a three-sphere theorem, like in complex analysis, then you can propagate smallness from smaller to bigger circles by using finite coverings. Okay, so we use the so this is the Isakov's Kaleman estimate, and for example, you can use it for convex functions. Okay, so our partial differential operator is like this. That's a general linear first-order equation. Assume that. So it says that, so the Kaleman estimate tells you that if, by using cutoffs, you can prove that if a solution vanishes on a circle like this, then it vanishes in the whole strip containing that circle horizontally. So how do we get this from the Kaleman estimate? So first step is to, because the weights are, you're only allowed to use convex weights. In the first step, you need to convexify your set. So you start with, so here is the function is small. You have to convexify it into some long, this kind of looking thing. And then you use the weights, which is approximately linear, and then you can propagate smallness horizontally. So instead of function being small here, you have it small here. And now it's kind of easier. This is space-time, right? Now it's kind of easier to believe that smallness propagates inside, right? So as soon as you convexify. So this is the transformation. Happily, it preserves the equation. So I do have still 1 minute. Thank you. I'll just breeze through I was trying to go slow this time. So we use the weights minus x. And then I will not go through all the estimates. You obtain the observability. Maybe just a comment. So I'll not talk about Navier-Stokes part, but there is a Kaleman estimate for the Navier-Stokes as well, and it's not, but okay, not for today then. Just about the number of zeros, how it's obtained for 1D Gevrey functions, because Gevrey functions can be compactly supported. Namely, I'll just tell you that the main trick is to approximate functions with interpolating polynomials, and again use Gevrey summability. So if you take enough many interpolating product, then even though this does not converge to the function, but there is an optimal stopping place. So instead of Schwartz lemma, there is this result with Ignatova, how to count number of zeros for Gevrey functions of order. Actually, if any order, there is a balance between the growth and the regularity. Okay, thank you very much.